9.5 Lesson 1 Alternating Series. We have two objectives for today. One, you'll know the conditions that a series must satisfy to apply the alternating series test. And two, you'll be able to apply the alternating series test. Vocabulary. We begin by thinking about what is an alternating series. And then we'll look at the alternating series test. So here we have this activity, write the first 8 terms of each series. And one thing to note is that in each series you have this part of it. And the part that I'm circling in green now is going to give you the alternation of signs. And you have the other part of it, which is just 1 over n for both series. So we start the index at n is equal to 1 in both cases, but in the first case we have negative 1 to the n power, and in the second case we have negative 1 to the n plus 1 power. So we know that if we raise negative 1 to an odd power, we'll get negative 1, and if we raise negative 1 to an even power, we'll get positive 1. So that's how we get the alternation of signs. So in the first problem, because we're starting at n is equal to 1 and we're raising negative 1 to the n power, for odd numbered terms we will get negative terms. So let's go ahead and take a look at that. So negative 1 to the first power is negative 1, so we'll get negative 1 over n. N is 1, so 1 over 1. For n is equal to 2, negative 1 to the second power will be positive 1, so we get 1 over n. N is 2. And then for n is equal to 3, negative 1 to the third power is negative 1, so we get negative 1, and then we have 1 over n, 1 over 3, and so on. So this is what is going on here in the first series. And it is an alternating series because you can see that you have an alternation of signs between positive terms and negative terms in our alternating series. So now we'll take a look at the second example that we're looking at. They both have the same nth term, 1 over n, but the difference is that in the first example, the odd numbered terms were negative, and in the second example, the even numbered terms will be negative. And we know that because the index starts at 1, and the negative 1 is to the n plus 1 power. So when you have n being an odd value, and you add 1 to it, n plus 1 will be even. So for odd numbered terms, you're raising negative 1 to an even power, so that will give you positive 1, and you get 1 over 1. This will become negative 1 over 2, and then you have positive 1 over 3, negative 1 over 4, positive 1 over 5, negative 1 over 6, positive 1 over 7, and negative 1 over 8. So these are two examples of alternating series. In alternating series, alternating terms have opposite signs. So again, what's an alternating series? Alternating terms have opposite signs. So the question that we have in this chapter is, if you have a series, how do you know if it converges or diverges? So if you have an alternating series, how do you know if the alternating series that you have either converges or diverges? We have something called the alternating series test, and of course the proof for this theorem ultimately goes back to the definition of a convergent series, which states that a series converges if its sequence of partial sums converges. And if you look at the proof that's provided for this theorem in your textbook, you'll see that the proof relies on the definition that I just stated. A sequence converges if its sequence of partial sums converges, and the proof uses a theorem from section 9.1 that states that a sequence converges if it's both bounded and monotonic. So the argument for the proof of this theorem is looking at the sequence of partial sums and arguing that the sequence of partial sums, because of the conditions that are stated for the alternating series test to be applicable, because of those conditions, the sequence of partial sums must be both bounded and monotonic, and therefore the sequence of partial sums must converge, and therefore, by definition, the series must converge. But that's if you want to look at the proof of that, that's what you would look for when you're reading the proof. But now we want to focus on applying the test. So when do you apply the alternating series test? When you have an alternating series, like we saw in the examples that we just looked at. So again, in the examples that we looked at, we had n is equal to 1 to infinity, and we had negative 1 to the n of 1 over n. And then we had from n is equal to 1 to infinity, negative 1 to the n plus 1 of 1 over n. So as we look at the alternating series test, I want to go back to the two problems that we started our activity with, and I want to show you which parts of the nth term are which parts that are identified in this alternating series test. So when we talk about a sub n, what are we talking about? We're just talking about the non-signed part of the nth term. So, and that's always going to be positive. So what gives each term a positive sign or a negative sign? The part that you see there. That's what gives each part a positive sign or a negative sign. Let me go ahead and highlight that in blue. And the reason I want to use blue is I can also highlight it here. So the part that I just highlighted in blue, that's going to make each term either positive or negative. But the rest of the nth term is always going to be positive. And that's what I had highlighted earlier in green. So the 1 over n is always going to be positive, but it is this part of the nth term that gives you either a positive term or a negative term. So that's how you understand that. So you have two possibilities for how you could have an alternating series, like we saw with our start activity. The first one, the index starts at 1, and you have negative 1 to the n power. So that's going to give you something like we saw earlier, where odd-numbered terms will be negative and even-numbered terms will be positive, like we saw with our first example. What you have here is like what we saw with our second example. And there we have an alternating series where the even-numbered terms are negative and the odd-numbered terms are positive. They are both alternating series. It's just that one has even-numbered terms being positive and the other one has even-numbered terms being negative. So in either case, you can use the alternating series test to determine if the series converges or diverges. And it states simply the following. The alternating series converges if the following two conditions are met. So if you want to know if an alternating series converges, this is what you have to check for, 1 and 2. You have to check for the limit of a sub n as n approaches infinity. So I'm going to label this problem as number 1 here, and I will demonstrate the alternating series test with this as my example. So if I want to know if this particular alternating series converges or not, I'm going to check for these two conditions. So for problem number 1, I'm going to check to see if the limit of a sub n. Again, what is a sub n? It's just the 1 over n. That's a sub n. So I want to check if the limit of a sub n as n approaches infinity is equal to 0. It is equal to 0 because as n goes to infinity, 1 over n will go to 0. So the next thing that I have to check for is the second condition in the alternating series test. Is it true that a sub n plus 1 is less than or equal to a sub n for all n? For all n, it could mean for all n greater than or equal to 1, or for all n greater than or equal to some fixed integer. So it does not necessarily have to be for all n greater than or equal to n is equal to 1. It could be true for all n greater than or equal to n is equal to, for example, 4. So how do you check for that? There are two ways you can check for it. You can check for it by algebraically comparing an arbitrary pair of consecutive terms, or you can use calculus. In this example, it's easy enough to algebraically compare an arbitrary pair of consecutive terms. Now, what does all that mean? It just means that you're going to consider an arbitrary pair of consecutive terms. For example, the fifth and the sixth, or the thousandth and the 1,001th term, or the millionth and the 1,000,001th term. So you're not restricting yourself to a fixed pair of consecutive terms, but an arbitrary pair of consecutive terms, so you can generalize that your conclusion is true for any n. So you want to check for that. So you want to check to see if a sub n plus 1 is less than or equal to a sub n for all n, greater than or equal to some fixed integer. In this case, we can show that this is actually true for all n greater than or equal to 1, where n is an integer, where n is an element of the set of integers. So how do we show that? Well, you just look at the nth term, which is 1 over n. So you should have 1 over n here. And then the n plus 1th term would simply be 1 over n plus 1. And is this relationship true? Well, we know that if we have two fractions and the numerators are the same, we can look to the denominators to see which one is going to be smaller and which one's going to be larger. For example, if you look at 1/4 and 1/3, we know 1/4 is less than 1/3. So the fraction with the larger denominator will be smaller. So n plus 1 is the larger denominator. So the fraction 1 over n plus 1 will be smaller than the fraction 1 over n. So this inequality is true for all n. 1 over n plus 1 will be less than or equal to 1 over n for all n greater than or equal to 1, where n is an integer. Having checked both of the requirements for convergence for an alternating series, we may conclude by the alternating series test that the alternating series for number 1 converges. So we can now state the conclusion citing the alternating series test. So there's our conclusion. Therefore, the alternating series converges by the alternating series test. So now we go to a second example. Here we have number 16, and we want to know if this series converges or diverges. And the first thing that you should do is to identify the given series as an alternating series. And the easiest way you can identify it to be an alternating series is by recognizing that this is a sub n, and the part that we are circling now is going to give you the alternation of signs. So because we have an alternating series, we can determine if it converges by using the alternating series test. So here's the alternating series test. We can apply it to determine if the series for number 16 converges or not. And we can apply it because we have an alternating series. So there are two conditions that we check for. The first one is right here. We want to check to see if the limit as n approaches infinity of a sub n. A sub n is n over n squared plus 1. Does that go to 0? And it does. And an easy way to determine that is you just look at what you have here, and this is a rational function, and the degree of the numerator is 1, the degree of the denominator is 2. So if the degree of the numerator is less than the degree of the denominator, your rational function will go to 0 as n goes to infinity. So this limit is equal to 0, and that was pretty quick. Now number 2, the other condition that you have to check for is this. Is it true that a sub n plus 1 is less than or equal to a sub n for all n? Or if not for all n, then for all n greater than or equal to some integer. The problem here is if you were to try to do it like we did for the first problem, here's what you would have. A sub n is just what you see here. A sub n would be n over n squared plus 1. A sub n plus 1 would be n plus 1 over n plus 1 squared plus 1. So it's not as straightforward as the other one. And the reason why it's not as straightforward as our first example is because the numerators are different and the denominators are different. You can compare the denominators if the numerators are the same, but here the numerators are different. So I'm not saying you can't do it like this, but it would involve more work. It's not as simple as what we did for the first example. So if you wanted to take an alternative approach, you can, and here's what you can do to show that this has to be true for all n greater than or equal to some integer. So basically, you want to consider the corresponding real valued function. The corresponding real valued function would be f of x is equal to x over x squared plus 1. And if you can demonstrate that the corresponding real valued function is decreasing for x greater than or equal to some fixed number, then you will show that this relationship for the terms of the corresponding series must be true. Because what this essentially means is that the terms of the series are getting, they're non-increasing. So either they're constant or they're decreasing. And you can show that they're decreasing by looking at the sign of the first derivative of the corresponding real valued function. If the derivative is negative on an interval, the function must be decreasing on that interval, and therefore this relationship must be true for all n greater than or equal to some fixed integer. So we can check for the sign of the first derivative. So the first derivative can be found by using the quotient rule. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the square of the denominator. So that's f prime of x. So we have x squared plus 1 minus 2x squared all over x squared plus 1 squared. And if you go ahead and combine like terms that we have in the numerator, x squared minus 2x squared would be negative x squared. So we have 1 minus x squared in the numerator. So we have 1 minus x squared in the numerator. And in the denominator, we have x squared plus 1 squared. So that's the derivative. And you can see that the denominator, because you're squaring a quantity, will never be negative. And the numerator for x greater than 1 will be negative because you have x squared that you're subtracting from 1. So if x squared is greater than 1, 1 minus x squared will be negative. And x squared will be greater than 1 for x greater than 1. So for x greater than 1, the derivative will be negative. So we just made an argument about that looking at the numerator and the denominator of the derivative. So because the derivative will be negative for x greater than 1, we know that the relationship that we're interested in for the alternating series test has to be true for n greater than 1. Basically, the function that we considered is decreasing, so when you look at the corresponding terms of the sequence, the a sub n has to be getting smaller each time. So we have that a sub n plus 1 must be less than or equal to a sub n for all n. For all n where n is an integer greater than or equal to 1. For all n where n is an integer and n is greater than or equal to 1. So what does that mean? That means we've checked to see that both conditions are satisfied for the alternating series test. We checked the first condition here, and we checked the second condition here. So by the alternating series test, we may conclude that the series here for number 16 converges. So let's consider this alternating series. This is an alternating series, as we can see from the negative 1 to the n plus 1 power. And here is a sub n. Does this alternating series converge? It does not. And the reason why it doesn't is because I know it doesn't because of the nth term test for divergence, but the alternating series test does not apply here because the first condition is not satisfied. We don't have that the limit of n plus 1 over n as n goes to infinity is equal to 0. In fact, that limit is equal to 1, and when that limit is equal to 1, I can use another test called the nth term test for divergence to conclude that this series must diverge, because the limit of a sub n as n approaches infinity is not equal to 0, and because it's not equal to 0, by the nth term test for divergence, we may conclude that this alternating series diverges. So the alternating series test does not apply because this particular condition is not satisfied. So here we have an example of an alternating series. You can see that the signs are alternating between positive and negative signs. So we do have an alternating series. And you can see that as n gets larger and larger, it does appear that the terms will be going to 0. However, the second condition is not satisfied for all n, because you can see that, yes, 1 is less than 2, and 1 is equal to 1, and 1/2 is less than 1, but then you have 2/3, which is not less than 1/2. So the second condition is not satisfied, so we cannot use the alternating series test in this case. So because of that, what are you going to say? You cannot really say anything. You just have to do some additional thinking to determine if this series converges or diverges. If the alternating series test cannot be applied, you just have to stop and say, I've got to do something else to reach a conclusion about convergence or divergence. So here, because the alternating series test does not apply, I cannot reach a conclusion about convergence or divergence unless I do some additional thinking and rationalization. In the first example that I gave a moment ago, the alternating series test did not apply, but I was able to use the nth term test for divergence to conclude that that particular series diverges. So today we looked at alternating series, and we looked at the alternating series test. You now know the conditions that a series must satisfy to apply the alternating series test. You have to have an alternating series. And we know what to do to apply the alternating series test. We check for those two conditions. And again, the alternating series test can only be used to conclude that an alternating series converges. If the test does not apply, you have to do something else to determine the convergence or divergence of the series.